So let us quickly look at the statement of that problem. A is a vector function. It acts on a domain R cross Rn and map it to Rm. Uh, so what we are having means we are having a claim that del f del x exists and it's continuous on this entire domain of definition. If it for a convex set W, a proper subset of D, there is a constant L greater than 0 such that for all the partial derivatives we can define that, then we can have this, and for T all, then we can actually claim that this function, this vector valued function actually is kind of means following the Lipschitz uh, one that. So first of all, here we need to prove now what I have discussed about this convex and other Holder's inequality. Let us consider that we define a non for any p in that range of and we find out q such that it satisfies 1 by p plus 1 upon q is equal to 1. So if that is the case, then we pick up t from the interval closed interval a comma b and 2 points in that set xa and xb from set W such that we define we define that line. I have already discussed a line gamma s 1 minus s x plus s xa plus s xb so this belongs to W for all s belongs to the set 0, 1. Now we take Z belongs to Rm. Actually Z is a vector that maps with the dimension of the image set. So what is that? We take Z, we take such that we are getting mod Z by Q is equal to 1. So it is not a very difficult assignment. We can find out such Q or such definition that yields Z Q is equal to 1, and also Z transpose f of t comma xa minus f of t comma xb is equal to, see here this one Z is what is dimension of Z? It's Rm. So if you take the transpose, it will give you 1 cross Rm, and f is something that is having a transpose Rm plus 1. So basically you will get here 1 cross m plus m plus 1. So that will result in 1 cross 1, and that gives you this one. norm P. How we can write that? Think about it, that how writing this is valid as long as we are considering. Now let us do one thing, that we set G S in such a manner that it is Z transpose F of T comma gamma S, where gamma S we have already defined it. Now by definition, GS is a real valued function. GS is a real valued function. Now GS is again let me define GS, that is Z transpose F of T comma gamma S So basically this one is continuous if we consider it in terms of gamma S, where it has S is something, it varies from 0 to 1 and Z is independent of S. So if you consider variation of GS over an open interval 0, 1, then you will find that or we can take the closed interval also, that doesn't make much difference. 0, 1, you will find that GS is continuously differentiable. Fine. GS is continuously differentiable. Now we can apply the mean value theorem. Mean value theorem states that G1 minus G0 is equal to G dash S1, where S1 belongs to 0, 1, right? So we can find out the two terminating value of S is equal to 0 and S is equal to 1, and calculating G dash S by chain rule, what we will get that Z transpose F of T comma XA minus F of T comma XB is equal to Z transpose del F del X T comma gamma S1 XA minus XB, right? So if this is the case, then we would like to exploit that Holder's inequality, like Z transpose omega is less than is equal to mod ZQ mod omega P. So if we use that, we will get what? That norm t comma xa minus t comma xb p less than is equal to, this one is how much? We have derived it. We set, first of all, when we set zq is equal to 1, then we set it like this gives us this. So this side will be, this is z transpose and this will play the role of omega. So we'll get it. Just a minute, let me check whether it's recording or not. Yeah, recording. Now this will give us less than is equal to mod zq mod del x t comma gamma s1 y minus xp. So this total thing can be written like, as we know zq is equal to 1, so this we can write L norm of, sorry, it is xa minus xb norm of xa minus xb. Now as both sides are having p norm, so we can set p is equal to 1 and that results in this. So hopefully it makes sense to you, like here we are getting, and we can have this because this we assume that del f, del f del x exists on that domain and that is less than by L. See, this line we can replace it because when we started defining our theorem, we said it, where it was, somewhere we must have defined it. Just a minute. Yes, here del f del x t comma x is less than is equal to L. So we have already defined that and that gives us this result. Anyway, the idea behind show you the proof is that which is valid for a single first order differential equation to find out its existence and uniqueness. At the beginning I gave you some intuitive idea, but now this gives us a concrete formulation that how we can extend what was true for a single means one-dimensional system or a system with one state variable. It's now valid for a system with n number of state variables. And also not only n number of state variables, it is valid for your output function also. Like if you do not have the state representation but only you know how your means state and input are related, you do not know the explicit rate of change of state, but you know that how the outputs are dependent on state and other things, then you can also figure it out. So we can have some example to enhance our understanding. Like I'm taking this from the book of Khalil. So here this function, it is clear that it is continuously differentiable on R2. So hence it is locally Lipschitz on R2. Now it is not globally Lipschitz since your del x is not okay. Let me discuss the theorem before I go to that. We can write if f of t comma x and del x t comma x are continuous, on the set then f is globally Lipschitz in x on comma b cross Rn if means if and only if del x is uniformly bounded on comma b cross Rn. So before I proceed further, I think instead of means showing you the proof, let us highlight a few means that terms that we have written here. Like one is what is uniformly bounded. So let me show you one example. A function sin mx. So this function is bounded by 1 for all values of m. You take any arbitrary value of m, you will get this is bounded by 1. So this function is uniformly bounded. However, if we take the derivative, then it will become m cos mx. This one is not uniformly bounded, although this one you can say that this is bounded by m, but the goal of finding uniform boundedness is that for any function f of x, we will find one finite real number m. Just let me check whether it's recording or not. Yeah. Finite real number m such that for all x belongs to D is the domain of the function, it may be Rn also if it is defined on the entire domain. This M holds good for all the points, right? So this one, this M cos M is bounded by mod M, but it is not possible to find out any capital M that satisfies that mod M cos mx is upper means bounded by capital M for all M belongs to R. Therefore, this one is not uniform bounded. That all the functions are not, this function is not uniformly bounded. So here let us again go back to that example from where we started, this one. So what you can see that this one is continuously differentiable or two. You find out the differentiation, that is m dash x. What you will get? Like basically you will get del fx del x, that is now here it is that this function is not globally Lipschitz. Why? Because it's globally Lipschitz if and only if del f del x is uniformly bounded on this. So let us check whether this one is uniformly bounded or not. See here, it is not possible for us to find out a value of m such that a finite m which can ensure that for all x1 comma x2 f of x will be, means norm of fx will be less than is equal to m. We can't find out such m, so it is not globally Lipschitz, it is only locally Lipschitz. Now we are interested in calculating the Lipschitz constant. For a constant set is given. This set, it is also a convex set. How this is convex, we will understand this also. The set description is so it is constant over the convex set. The set description is given. Now it is clear that if you consider this in a two-dimensional space, it will take a shape of ellipse for different value of x1 and x2, and for x1 is equal to x2, it will take the shape of a circle, right? So even if it takes a shape of ellipse or a circle, obviously any such kind of shape will always give you, or will always form a convex set. Like any point on that set, you can connect them, or whether they are connecting line will also become a member of that set. So we'll have that Jacobian matrix value del f del x is equal to this much. Now now we have to find out the maximum value for which this will remain finite. Okay, so here actually we need to calculate matrix norms. I'll show you how to calculate matrix norms for different purposes and how to calculate. So just with this, let me move to the next example of a system just a minute. Now here, in order to understand the concept of norm for this matrix, we need to know a new concept that is known as induced norm. Once we discuss induced norm, we will be ready to understand the more advanced concept. So what is induced norm? Like we can have, let us first consider a square matrix. This is actually means a complex matrix. Like one matrix, if you have like this 1 plus 4j minus 2j 2j 3, so this you can say that this belongs to C 2 cross 2. So this is the very basic idea. Now similarly, we can define it for means we can have it for real matrix also. What is there that we have already started that these matrices, or means these are actually linear vector space. So this is linear vector space. Now this, if we consider an element a square matrix belongs to this C n cross n, then we can define a rule for mapping. Like we can define a linear mapping alpha from c to the power n to c to the power n, right? Basically we can write alpha x is equal to ax for all x belongs to c to the power n. So this is one, like if you want to understand what I am trying to say, let me just give you one example. Let us take, I am doing it for real number, that makes it easy. Now if we have something like then what you will have, you will have it like 2 minus 2. So basically you can visualize this 2 minus 2 like a function that is doing something to, means we can define a function that takes argument 1 2 and produces this 2 minus 2. So we have to figure out what is that function. Obviously that function, we can say that function is so defined. If we say that function, if we break it in two part, so we can write this one is 2 into x1 and the second one is 4x1 minus 3x2. So whatever argument you pass, it will be like this, and this whole thing can be written as a linear function alpha of x1 comma x2. So that is what I am trying to say here. Now another thing what we can have is that we can write every linear mapping beta from Cn into itself. You can associate it with an n cross n matrix B belongs to C n cross n. Like, let us consider that Ej be a vector in Cn which has all 0 component except the jth component which is equal to 1. So Ej is how, what is Ej? Ej is like 0 0, here this is the jth element, it is 1, and then remaining are 0. So this we can now write beta Ez will also belong to Cn so accordingly you have beta with different value of Ej. So what you will get, you will get B1j, B2j, Bnj, suppose defined as vector Bz transpose. This is a vector, right? So we can define Bj in this way, and from that what we can write, B is what? B comprises all such vectors like B1, B2, and at the end Bn. So we can easily verify that beta x is equal to Bx for all x belongs to Cn. This one-to-one correspondence is actually important for induced matrix. Please pay your attention that induced matrix definition is that let then for all A belongs to Cn cross n, the quantity Ai, that is defined as supremum now. If you find a vector for which its norm is 1, then it will become supremum of Ax. So this will be is equal to supremum of x then is equal to 1 norm of Ax. This is called the induced matrix or induced norm of A corresponding to what we are familiar with, the vector norm, right? Now what it basically tells us, like we can verify that whether this norm is satisfying all the properties of norm or not. Like we can show that if norm of AI greater than is equal to means is equal to 0 for all A belongs to Cn cross n. Why so? Because what you are actually doing here, try to understand that if you multiply it with a means vector, then what actually you are doing here? Think about it. What operation you are carrying out? Let me give you one example. Like we can write out the norm for vector, and we'll find out the corresponding norm for the matrix. So norm on your Cn, and here we'll have induced matrix norm on C n cross n. So here it is how much you can have here it will be maximum I mod A I J. So basically, sorry, you have to take the row sum. Like if I give you one matrix -1 -3 0 -2 0 4 -5 -6 0, then basically you will have maximum of j in that 1 to 3. So here what are the row sum you will have? For here it will be 1 plus j. Then actually, since you are considering max, there will be, the whole thing will be boiled down to like this: 1 mod 1 plus mod 3, that is coming from when j is equal to 1. Now there will be like in the next -2 plus mod 4 j is equal, sorry, this is I is equal to 1, I is equal to 2, and then for I is equal to 3 we will have -5 mod plus, sorry, mod of -5 plus mod of -6. This is for I is equal to 3. So you will have, if you evaluate the result, it will give you 11, right? Now you can see that if you change it, then also the result remains same. Now this is your induced norm AI infinity. Now likewise, if you want to have fast norm or taxicab norm, what you do is that you just go for the summation. Here what you need to do is that so basically what you do, like the previous one, you can consider it as row sum, and this time you need to find out the column sum. So if you do column sum, what you will get here, max. So for the first column it is then -3, then it is 4. So your this value will become 9. For the same matrix we are doing the calculation. Now what about Euclidean norm? That is so here you will get so A star is complex conjugate of A. So basically what we need to do here, if we take this matrix, now this gives us what? This gives us, you have to figure out this is A. So you have to first find out A transpose A, that is so if you do it you will get that will be 1 square to 4 square to 5 square, so it will give you 30. Then here you will have 3 plus 30, that is 33. Here you will have -8. Similarly, you can expect this matrix to be symmetrical. So only things we need to calculate is that these two corner element and this one. Rest of the element we will see it will be symmetrical in nature. So this one, how to find out this one, we will get it like 3 square plus 6 square, so 9 plus 36, it will be 45, and this one will be how much? This one will be 0. So, and this we need to find out. This will be how much? 16. This will be 0. This will be 33. This will be minus 8. If you want, you can check it, that you will get surely 33 here. If you do it, that will result 33. And similarly, if you do correct calculation, this should result minus 8. Now what is needed, that we have to find out the maximum eigenvalue. So for this you will find out 3 eigenvalues, and whatever be the maximum eigenvalue, that will give you your second induced norm for your matrix of this one, right? So you get certain idea about this matrix norm. Now let us go back to our original example. There was a whole lot of noise in the surroundings. So what we can see here, that from where we started all our discussion, that del x is equal to 1 plus x2 minus x2 1 minus x1. So here what we can do, we can figure out their so what you will have here, right? So if this is the case, then all the points in W that satisfy minus 1 plus x2 plus x1 is less than is equal to 1 plus a2 plus a1, and absolute value of x2 plus 1 minus x1 less than is equal to a2 plus 1 plus a1. Then we can figure out that del x induced infinity norm is less than is equal to 1 plus a1 plus a2. Do note that here any norm you can select to find out the boundedness of the matrix, you can select any norm, because we know norms are equivalent. Like if you figure out something for two norm, then that will be also true for infinite norm, and also true by using derivation based on first norm. So one norm, that is we are going to see it in that another example. Let us consider a function f of x is equal to so this function clearly is not uh, continuously differentiable on R2. However, we can check the Lipschitz property by doing similarly fx1 minus fx2. So what we'll get here, that uh, if we take saturation function, the typical property of saturation function is that so this is the typical nature of saturation function, and if this satisfy, then what we'll obtain? We'll obtain norm of f of x a x b. Let it be xb whole square, is 2 norm square, is less than is equal to xa minus xb square plus this much we can write. How this is valid? Because if you add these two, like we know it is means norm of so we are applying that same thing over here, like uh, we are having some function and we break them into part and getting this. Now what we will see, that if we further means proceed with this step, then we'll get this is equal to right? So we can means here we can exploit the matrix second norm property, like what I'm trying to say. It is taking the shape a square plus 2ab plus b square. If you observe it carefully, where a is this much, b is ab is this, and b is this, so that can be written. So that is less than is equal to lambda max of this, if this matrix is say M, lambda max MTM into 2 norm of AB whole square, or means you can take this also AB square. Yeah. So this is what we will get. Now if you try to find out this matrix lambda max, you will get lambda max will be 2 point root under 2.168. This is the maximum value of MTM eigenvalue. So we can write it like norm of Excel. Right, for all xa comma xp belongs to R square. Actually, this is a property we have used. This is this. If you see this M, this is a positive semi-definite matrix, and this positive semi-definite symmetric matrix, that is always upper bounded by its maximum eigenvalue. So the present matrix is also positive definite, but for this structure we can gradually get a positive semi-definite matrix also. But the important thing here is that for any positive definite or semi-definite matrix, it is always bounded by the maximum eigenvalue, and I hope you know that for positive definite or semi-definite matrix, your its means eigenvalues are always positive, right? Anyway, I hope you gather some idea. In our next video, we'll discuss more on some other advanced topics.